Dear students, so in the previous lecture we talked about entropy, and we said that entropy is the impurity in information. So as it was like, just to give you example like this one. So like high impurity or high entropy in the right basket, and less impurity or less entropy in the left basket, right? So, so when the entropy is less, the predictability is higher. When entropy is higher, the predictability is lower, right? So this is like inversely proportions. And then we talk about how to calculate the information gain, right? And then with the help of the entropy, so this is the formula for information gain: entropy of x minus entropy of x divided by x entropy x of v, and then we different values. And this is the normal calculation, that how we calculate the entropy and the information gain. So this is the information gain, which is 0.521 for this one, and usually we compute entropy only once, right? This is the algorithm ID3 algorithm. It's also like, based on the entropy values and majority label as well. So here, like, all the points have the same class here. So this is like, ID3 full algorithm in Python. You can find the exact code on Kaggle, or you can find the exact code on GitHub. So there's another one which I discussed in the part one of this machine learning algorithm decision tree, that along with entropy we have a Gini impurity, which is measured in a different way, and it has like different connotation, but it also measures the impurity, and it works with the probability and one minus summation of the probability square. So square is important here. In the previous one there was no square; it was just like, there was like log, but here there is no log here. So Gini impurity, what is the Gini impurity? Gini impurity measure how often a randomly chosen example would be incorrectly labeled if it was randomly labeled according to the label distribution. So error of classifying randomly picked fruit with the randomly picked labels, right? So yeah, now here is like, in Gini Index, you can see labels on the right hand side and the fruits on the other side. So we have orange apple, and so what does Gini Index? So Gini Index measures how often, like, randomly chosen example. Like for example, we have orange on the left hand side. We have this, like, chosen example like orange and an apple, and it will be like, incorrectly labeled. And if it is incorrectly labeled, right, according to the label distribution, yeah. So so by this way, yeah. So here, what's the formula for this one? It's a square, probability square for the set of example x with k classes, 1 minus this one, where pi is the proportion of elements of class I, right? Okay. And here you can see entropy is higher, and the Gini index is like with 0.5. So you can see the difference between entropy and Gini index, and how it, like, works differently. Can be used as alternative to entropy for selecting attributes, right? Yeah. So best attribute is the highest impurity decrease, okay, and then we have color and fly, and then we have Gini index, okay, and this one with the Gini X colors, and then how we find all this one. So this is like, you just need to compute the values, and how we find this 3 by 7. 7 are the total elements. If you count in the table, the total elements are 7. 1, 2, 3, 4, 5, 6, 7, right? And three are like, mammals, and four are birds. So that's why 3 by 7 and 4 by 7. And by this way you can easily calculate and by computing in the formulas. So for the fly, the Gini is 0.275. Okay. So entropy versus Gini index. Entropy and Gini impurity give similar result in practice, basically. Theoretical comparison between Gini index and information gain criteria. Entropy must be lower to compute because of the log. Yeah. So because, as I told you, that log reduces the things, because that's why entropy must be slower to compute. Pruning is very much most important. So there are two kind of pruning in the decision tree. One is called pre-pruning before the applying the algorithm. Another is called post-pruning after the algorithm. Sometimes we need to remove some of the leaves which is not significant, which is not like giving the correct results. And the last topic would be then missing values, how to complete the missing values in the tree. Okay, so pruning is a technique which reduces the size of the decision tree by removing the branches of the tree, which provides little predictive power. So, if there are predictive power, which we sometimes call in statistics F score, like if the F score is down, so just remove it, right? It is a regularization method that reduces the complexity of the final model, and thus reducing the overfitting. Okay, so decision trees are prone to the overfitting, they are yeah, so they are there is overfitting problem. Pruning methods, so decision trees are prone to the overfitting. And then what are the pruning methods we have it? We have pre-pruning, stop the tree building algorithm before it's fully classified the data. So as I told you that one is pre-pruning, and then it's called post-pruning. Build the complete tree, then replace some of the non-leaf nodes with the leaf nodes if that improves the validation error. Pre-pruning, so here you can see that how the pre-pruning works. Okay, if some condition is met, the current node will not be split even if it is not 100% pure, right? Okay, so if 54% is yes and 5% is no, I think that there is no further pruning needed. It will become a leaf node with the label of the majority class in the current set. Common stopping criteria includes like setting a threshold on, like we have entropy, we have a Gini impurity of the current set, and then we have a minimum threshold on entropy, which is like for example 0.4 here it's selected, and stop even if node cannot be split. Yeah. So the confidence value is 91.52%. We will see that how we found the confidence value. And the class distribution, it could be used as a prediction confidence as well. And number of samples in the current sets, gain of the best splitting attributes. So these are the different criteria which you need to fulfill or you need to check. Depth of the tree, means how many levels of the roots are there. Post pruning is the one when you do it. For example, there are some nodes which are not significant, and then you remove it. Prune nodes in the bottom up manner if it is decreasing the validation error. So if the validation error is more, then remove that nodes. Okay, so here number of prunes nodes, and the graph you can see how it is the validation error is converging. Here is more convergence. Yeah. Handling numerical attributes, yeah. So yeah, numerical attributes is easily to be handled. Yeah. So here, what are the numerical attributes? Let's see what are the numerical attributes. Humidity is a numerical one. Other are categorical, like outlook is a categorical, temperature is a categorical, wind is a categorical, and the label, which is called the plateness or no, it's also categorical. Any numerical attributes would almost always bring entropy down to zero. Yeah, that's because of the log factor. This means it will completely overfit the training data. So numerical attributes have to be treated differently. Find the best splitting values. Gain of numerical attributes A is if we split it at value T. Okay. And then we need to sort it. Okay. And then we have mean of each consecutive pair. And then we have this one. So you can see how it works, like how we deal with the numerical values. And here the gain is 0.94. And you can see how the things are changing with the criteria. 83 is the best splitting value with information gain of 0. This one. And then we have 83.5 is the best splitting value for humidity with information gain of 0.152. Humidity. So these are some more information. Humidity is now treated as a categorical attribute, you make it greater than and low and less than, so it works like in a categorical. A new optimal split is computed at every level. So decision tree works very good in the categorical one, but not good in a numerical one. Numerical attribute can be used several times in the tree with the different split values. Yeah, the last topic is about the handling missing values, which is very much important. So how we compute it. So there are different ways to compute the handling missing values. One of the most important criteria is missing values to have simple is you can ignore it sometime, but sometimes you cannot ignore it. Why? Because you will throw a lot of information. There are better ways for missing values. Set the most common values, some average values, sometimes set the most probable value in the label, right? So that could also be, yeah. Add new instances for each possible values, leave them unknown, but discard the sample when evaluating the gain of the attribute. If the attribute is chosen for splitting, send the instances with the unknown values of the children. Build a decision tree on all other attributes to predict missing values. Okay, and use instances where the attribute is defined as a training data. Yeah. So yeah, for the loan, let's suppose loan is missing, not a student, 49 years old, unknown income, fair credit record. And this one, when we encounter a node that checks an attribute with the missing values, we explore all possibilities. Yeah, we explore all the branches and take the final prediction based on the weighted vote for majority, or weighted majority we call it in a technical way, of the corresponding leaf nodes. Yeah. C4.5 algorithm is very popular and is one of the best algorithm in is an extension of ID3 algorithm, which brings several improvements, ability to handle both categoricals and numerical value, both, because as we saw that numerical values were not properly handled by the normal decision trees, and continuous attributes are split by the finding a best splitting threshold values, and ability to handle the missing values both at the training and inference time. Missing values at training are not used when information gain is computed. Missing values at inference time are handled by exploring all the correspondent values branches, and the ability to handle attributes with a different cost. And the last but not the least is the post-pruning is the bottom-up manner by removing the branches that decrease the validation error. So validation error is very much important, and it increases the generalization capacity. So boundaries, if you look at the boundaries here, so what are the different boundaries for support vector machine and the decision tree? So decision tree is like you can say stepwise, and support function is a hyperline. So hyperline is either like across the border, while decision tree is a step line. So decision tree produce non-linear decision boundaries, while support vector machine is very straightforward, right? And then we have like training and inference. Like from here you can do the training and take the inference, and decision tree algorithm is done. Yeah, inference, we can take inference for the either apple or orange. Yeah, this is the history of the decision tree here. Okay, you can see, you can learn more about these references. So summary, so in the summary what we learned, yeah, so today we learned about decision trees. So decision tree, like it represent a tool based on the tree-like graph or decision and their possible outcome. Decision tree learning is a machine learning method that employs a decision tree as a predictive model. ID3 builds a decision tree by iteratively splitting the data based on the values of an attribute with the largest information gain, decrease in entropy. Using the decrease of Gini impurity is also commonly used option in the practice. C4.5 is an extension of ID3 that handles attributes with the continuous values, like its missing values, and add regularization by pruning branches likely to overfit. So these are like the summary of this whole chapter. And along with that one, we have some advanced form of the decision tree, which called random forest. We call ensembling learning with the decision tree. So we have like random forest, which where we have like aggregate all the trees. There are some approaches which is called bootstrap aggregation, or we call as a bagging method, or bagging. So we like bag all the data items, and there are different algorithms like DT learning, DT algorithms, like and apart from this one, inference can also be done with a different confidence percentage. And here the different methods you can see here. And random forest, this is one of the sample example. It is all the combination of the different decision tree. So this is like more references, and this is the end of today's session. So see you in the next session with a support vector machine. Thank you.